All right, today we are going to add another test to our list of tests for convergence or divergence. But before we jump into that, I actually want to review a little bit about geometric series and interval of convergence. So go ahead and pause the video and work through the first 6 warm-up problems. All right, so the top 3 problems, we're identifying that R value, we're talking about how it relates to 1. Is it greater than 1? Is it less than 1? And that helps us identify if it converges or diverges by GST. And then on the bottom 4 problems, we have variables with our ratio. So we're identifying which x values create a ratio that will converge, and we're identifying that interval of convergence. So that was a little bit of review. But the reason we want to talk about geometric series is because that's going to lead us into our next test. And our next test is called the ratio test. The ratio test. And it makes sense to talk about geometric series when we're talking about the ratio test because the geometric series is defined by a ratio. And in general, how do we identify that ratio? If I gave you a list of terms like 2, 4, 8, ... If you could not immediately tell what the ratio was, we always tell you to take a term and divide it by the term before. That's how you find the ratio. So take a term and divide it by the term before. That's how we can define our common ratio. Every series has a ratio between consecutive terms. That ratio just might not be common. So what if my series, and I should write this one as a series since I didn't put plus signs here. What if my series was 2 plus 5 plus 9 plus 16 plus ... I still have a ratio here, just the ratio is changing if I look at these 2 terms versus if I look at the next 2 terms. The ratio is changing. So how does that help us? Before we jump into what the ratio test says, let's go ahead and look at an example series and think through what we know so far. So let's consider the series from n equals 1 to infinity of n to the 10th power over n factorial. Now, this is not geometric and it's not alternating, so we can't use AST and we can't use GST. We could possibly use NTT. However, actually, let's look at this. If we took the limit as n approaches infinity, this looks like it would be going to 0, that limit, which would mean that NTT would be inconclusive. So the 3 tests that we have learned so far either don't apply or are inconclusive for this particular series. So let's consider looking at the behavior of the R, which we defined up here. How does this R change as we go towards infinity? So let's go ahead and look at that. So let's look at the limit as n approaches infinity of, the n plus first term would mean that I'm just plugging in n plus 1 everywhere that there is an n. And I'm going to divide that, and I'm going to write it this way. I'm going to divide that by the a sub nth term, which is just what we get when we have n plugged in. Now, I'm going to put brackets around this. Now, is there anything that can simplify? Well, we learned a very long time ago that we can simplify this division by flipping and multiplying our second term. So that would give me n factorial over n to the 10th. I'm going to invade down here a little bit. So the limit as n approaches infinity, well, n factorial and n plus 1 factorial, that's going to simplify. That's going to leave just n plus 1 in the denominator. And I can't simplify these n to the 10ths here. Oops, the top is actually n plus 1 to the 10th, which is why I can't simplify them. But what's happening with this limit as we go to infinity? This is to the 10th degree. If I multiply these, this will be to the 11th degree. So n to the 10 over n to the 11, that's going to go to 0. And you might be thinking, well, this isn't helpful if the limit goes to 0. But actually, this is helpful if we're considering this geometrically. Even though it's not geometric, we're thinking about this ratio, even though the ratio is not common. What we're saying is, as n goes to infinity, this is going to 0. And what does 0 tell us? If this was a geometric series, we could say that 0 is less than 1. So we could conclude that this converges. And that's what the ratio test does. It compares the ratio of the n plus first term over the nth term, and it analyzes how that limit as n approaches infinity behaves. Is it going to 0? Is it going to infinity? And the conclusions that we can draw from the ratio test are very, very similar to the geometric series test. And what I mean by that is we can actually conclude convergence or divergence, and we're looking at how the behavior is in relation to the number 1, just like with GST. The one issue here is that if that limit is actually equal to 1, then we don't have anything. So there is still a possibility that this test won't always work. If the ratio is equal to 1, or if the limit, I should say, if the limit is equal to 1, it can still be inconclusive. So in order to use the ratio test, which I also want to point out, the ratio test is incredibly helpful if you have factorials or exponential functions and none of the other tests work. What you can do to use the ratio test is you can take the limit as n approaches infinity of the n plus first term divided by the nth term. If that limit simplifies to be something that is less than 1, the series will converge. If that limit simplifies to be something that is greater than 1, or infinity, that series will diverge. And if that limit is equal to 1, this test is inconclusive. One thing that I didn't really mention that you will see, there is the absolute value around the terms in case this series has some negative numbers and things like that. You're just going to take the absolute value of that ratio, because just like with GST, we take the absolute value of r and compare it to 1. We're going to take the absolute value of r and compare it to 1 in the ratio test. So let's work through some examples. So for number 1 here, I'm going to take the limit as n approaches infinity of, I'm going to plug in n plus 1 everywhere that there is an n. So 1 over n plus 1 factorial divided by 1 over n factorial. I'm going to flip that, the limit as n approaches infinity of 1 over n plus 1 factorial times n factorial over 1. And then I'm going to go ahead and simplify that. That's going to give me, well, the n factorial is going to make that factorial divide out. So 1 over 1 plus n. This limit is equal to 0 as n goes to infinity, and 0 is less than 1. Therefore, this converges by the ratio test. All right, let's do another one together, and then I'll give you some time to work on 3 through 5 on your own. So the limit as n approaches infinity of the absolute value of 3 to the n plus 1 over n plus 1. I'm going to just start by flipping my fraction. So times n over 3 to the n. I'm going to simplify. 3 to the n is going to make that go away, so I'm just going to have 3 left in the numerator. I can't simplify this n and n plus 1, so 3n over n plus 1. As n goes to infinity, that degree of that polynomial is the same in the numerator and the denominator, so this limit is going to be equal to 3. 3 is greater than 1, therefore this diverges by the ratio test. Why don't you go ahead and pause the video and work through 3 through 5 on your own. So for number 3, if you work through the ratio test, you actually get that limit is equal to 1, which means the ratio test is inconclusive, and at this point, we don't currently have a test to use on that problem. We will get to that later in this unit. All right, number 4 has some factorial work that you need to do. You need to make sure that you distribute this 2 to the n plus 1 when you're substituting that in, and that you simplify the 2n minus 1 factorial over 2n plus 1 factorial in the denominator there. So that limit is 0. 0 is less than 1. Therefore, this series converges by the ratio test. And lastly, for number 5, we can look at that limit. A lot of stuff simplifies out. So the limit as n approaches infinity is going to be 4 over 5, which is less than 1. Therefore, this converges by the ratio test. So we have applied this idea of looking at the ratio just as we did with the geometric series test to a non-geometric series. What we're going to do now is extend the idea of the interval of convergence, as we did with the geometric series, to a non-geometric problem. So let's go ahead and look at that. So in Unit 7, we looked at a geometric power series where we had a ratio that could be represented geometrically, and we set the absolute value of that ratio to be less than 1 so that we could identify the interval over which there was convergence. We're going to approach this in the same way. We are going to use the ratio test to find the interval of convergence for a non-geometric power series. The only problem is that a geometric series cannot converge at its endpoints. That's why we say that the absolute value of r must be less than 1. It can't be equal to 1 in a geometric series because then it wouldn't actually be a geometric series. That is not the case with a non-geometric series. We have learned already in this lesson that the limit could equal 1, which means it could converge, and we don't have enough information yet. So we're going to talk about not the full interval of convergence, we're going to talk about the radius of convergence. We're going to almost talk about the full interval of convergence. Today we're going to focus on the radius of convergence, and then later on in this unit, once we have learned a few more tests, we will wrap this up with the full interval of convergence. So what is the radius of convergence? The radius of convergence is the distance from the center to the interval on either side. So you could think of it as it's the interval of convergence, the length of that divided by 2. And something important to notice is that every single power series converges at least when it is equal to its center. So even if we're getting something that isn't giving us a full radius, it's possible that the radius is 0, but it converges at that value, which is the center. Let's look at some examples and try and solidify this in. Why don't you go ahead for the example below and first perform the ratio test on the series that we're given. So we're going to take the limit as n approaches infinity of x minus 3 quantity to the power of n plus 1 over 2 times n plus 1 divided by or multiplied by the reciprocal of our original general term, the nth term. Now what I want to remind you is that x is not what is changing. X is a constant, so x minus 3 we're not plugging in x plus 1, we're plugging in n plus 1. So let's go ahead and simplify this a little bit. So we can divide the 2 out. We can simplify our x plus 3 to the nth power to x minus 3 to the nth power to just be x minus 3 in the numerator, and we're left with this limit expression. As n goes to infinity, this is going to the absolute value of x minus 3. And remember, that absolute value, or that x value, isn't changing as n goes to infinity. Well, this is great. We need to be able to identify the ratio that over which interval it converges. So what we're going to do is we're going to figure out what values of x make this statement true, just as we did with a geometric series. So you always need to start with the ratio test, identify what that ratio is after you take the limit, and then figure out where this converges. So this is going to be, if I perform a little algebra over here, if I add 3 to all the sides, that's going to give me 2 is less than x is less than 4. Okay, so here's what I was mentioning before, but I'm going to try and show you a little bit more. It is possible that this series could actually converge at those endpoints, and we are going to talk about that in a later section, which is why for right now I'm not going to ask you what the interval of convergence is. I'm going to ask you what the radius of convergence is, meaning how far out do I go from the center. So to get from 2 to 4, that distance is 2, the full distance, so the radius would be equal to 1. The radius of convergence is 1. We go 1 unit from the center. We will learn more tools to identify the full interval of convergence in future sections. All right, let's work through some more specific examples, and then we will look at a more abstract example and talk through that one. So for all of the problems from 10 through 15, the very first thing you have to do is use the ratio test, and you should state, as I did up here, by the ratio test, this is what we are about to do. That will give you the absolute value of your ratio, and you need to set that less than 1, and then figure out what your radius of convergence is. The amount of math that you need to show here is sort of dependent on how long it takes you to get there. I want to see the ratio test. I want to see this absolute value is less than 1, and I want to know what the value of the radius is. So let's look at number 10. So I added a couple of reminders here. You must do the ratio test first, and that the radius of convergence is the distance from the center to either endpoint. So let's go ahead and do the ratio test here. We're going to take the limit as n approaches infinity of the absolute value of 4x quantity to the power of n plus 1 over 4x to the power of n. Well, that's going to simplify to just be the limit as n approaches infinity of the absolute value of 4x, which is the absolute value of 4x. As n goes to infinity, that's not impacted at all. So we know that we want the absolute value of 4x to be less than 1. If right now you can already tell that the radius of convergence is going to be 1/4, that's fine. You don't need to show any more work. If you don't see how far this is going to be from the center, you can go ahead and split it and then divide by 1/4. The radius of convergence is the distance from the center to either end, which is 1/4. Let's do one more together, and then I'll have you pause the video and work on the remaining 4 on your own and bring us back together to do 16. So the limit by the ratio test, what I'm about to do is all by the ratio test. The limit as n approaches infinity of the absolute value of this to the n plus first. I'm going to multiply by the reciprocal of the general term. And then I'm going to simplify what I can simplify. So this can go away. I'm just going to have x plus 4 in the numerator. And I'm also going to have, my 3 is going to be gone, and n up here. So the limit as n approaches infinity of the absolute value. In the denominator, I'm going to have n plus 1, and I'm going to have 3. As n goes to infinity, this goes to 1. So this is going to leave me with the absolute value of x plus 4 over 3. We want that to be less than 1. Again, if you can tell right now that the radius of convergence is going to be 3, I think you don't need to show work there. Otherwise, -1 is less than x plus 4 over 3 is less than 1. Multiply everything by 3. Subtract 4. It's less than -1. How far is it from the center to -1? It is 3. You could also think of it as how long is this entire interval from -7 to -1. The length is 6, and half of that is 3, if that's an easier way for you to think about it. All right, I encourage you to pause the video and go ahead and work on 12 through 15 on your own, and then unpause the video and see how you did. So on number 12, once we perform the ratio test and simplify a little bit, we get here. And note that n to the third times this, I'm going to have an n to the fourth in the numerator, which means this limit is going to be infinite, which means that this is greater than 1, which means this series diverges by the ratio test. But remember, every series converges at its center, so there is a radius of convergence, and the radius of convergence is 0. And the value for which this converges, it converges when x is equal to 0, and I can see that up here, the center is 0. There's no x minus something or x plus something in parentheses to the power of n. So the radius of convergence, which is what this question is asking for, is 0. But this series does converge, it just only converges when x is equal to 0. For number 13, I included the alternating piece inside of absolute value, but you really don't need to do that because it doesn't matter. No matter what, it's going to be 1 or -1, and then we're going to make it positive when we take the absolute value. So the alternating part here is pretty irrelevant. What can we simplify? X to the n and x to the n plus 1 is going to leave us with just x in the numerator, n squared in the numerator, n plus 1 squared in the denominator. So the limit as n approaches infinity of that is going to be the absolute value of x. Absolute value of x. Whoops. There we go. We need that to be less than 1. That means our radius of convergence here is going to be 1, the distance from the center to either endpoint. So number 14, the tricky part really occurs when you get to this absolute value of x minus 4 quantity squared is less than 1. Well, you can get rid of the squared sign. I'm going to square it. It's always going to be, regardless of the absolute value, you can solve x minus 4 is less than 1. But in reality, how far is this from the center? It's going to be 1 unit from the center. So the radius of convergence is 1. And then 15 is a little weird because once you get down, you get that the limit is equal to 0. This is less than 1. And the reason the limit is equal to 0 is because the denominator is going to infinity while the numerator isn't changing at all. This is always less than 1. Therefore, this converges always by the ratio test, which means that the radius is infinite. And actually, I want you to pause the video and look at this series. What is this series? Do you know this series? You should know this series, and this series is e to the x, and we did know that e to the x does converge everywhere, so it's kind of nice to verify that using the ratio test here. Okay, let's look at this last question together. We have an abstract power series, c sub n of x to the power of n, and we are given that this power series is known to converge at x equals 2 and diverge at x equals 5. So a couple of other things to notice about this series is that we can tell immediately that our c is equal to 0 based on this. There's no x minus anything. It's just x to the power of n. So our center is 0. If we know that it converges at x equals -2, question A is asking us, what is the smallest possible radius of convergence? Well, we know that it can go all the way down to 2 and converge, which means the smallest radius of convergence is 2. And you'll notice that what I don't know, and we're going to come back and talk about this when we get to part C, but what I don't know is what's happening at +2. I don't know if it converges at +2, so I'm going to leave that as a red question mark for right now. Part B says, what is the largest possible radius of convergence for this series? So we know that it diverges at x equals 5, which means we know if I was to write an inequality involving our center and 5, and remember it's centered at 0, and if it is centered at 0, that means that the left bound should be -5, less than -5. We don't have any information about what's happening at -5, so it is possible that it converges at -5. It's not possible for it to converge at +5, so the largest possible radius of convergence is -5. Let's try and wrap this all up on part C. We are given a bunch of different values for x, and we're being asked if it diverges, if the series diverges or converges for each of those following values. And I'm actually going to set up a little table to make it easier for us to organize our answer and then talk through each specific case. Okay, so I've set up my table here. I know that the largest possible radius is 5, which means the smallest number that could possibly converge, which we don't know about yet, is -5. -8 is below that, so that's outside the interval, so -8 is definitely going to diverge. -5, we don't know. We don't have enough information yet to conclude what's happening at x equals -5. -1 is inside this interval that we know converges. It's between -2 and +2. That means that -1 will converge. Similarly for 0 and 1, all three of those numbers are within the smallest interval of convergence that we can be considering based on the radius. +2 we don't know about. We don't have enough information to conclude. We only know what's happening at x equals -2, so it could converge there, we don't know. Similarly, we know that it diverges at 5, but we don't know what's happening between 2 and 5. We don't know what's happening between 2 and 5, which means it could converge at x equals 4. We just don't have enough information to conclude that yet. So think about the radius of convergence, about how far out we're going from our center value to help us determine if something converges or diverges. So big ideas wrapping up this section. Looking at a non-geometric series by considering its ratio and performing the ratio test to determine if that ratio, as n approaches infinity, is less than 1, the series will converge. If it's greater than 1, the series will diverge. And remember that the ratio test can be inconclusive if that limit is actually equal to 1. Then we don't know what's going on, and we're going to need another test to help us out there. And then we focused on the back of these notes about the radius of convergence for a power series and how we use the ratio test to identify that range by which our ratio, x minus 3 or x minus 5 or whatever that ratio happens to be, needs to be, the absolute value of that needs to be less than 1, so we can identify our radius of convergence. And we will build on this idea to find the full interval of convergence after we have learned a few more tests for convergence. Make sure you write down any questions you have, and I look forward to supporting you on this in class. Thanks for listening.